All right, welcome back to another lecture. We're going to get started on Unit 4. There are only 3 lectures that we're going to cover in Unit 4 because the rest of the unit is going to be working on some projects. But the 3 sections that we're going to cover in the unit are all about association, determining when two variables have some kind of relationship with each other, when there's some kind of dependence or association. So all of these are kind of synonymous terms. And we're going to start, the way you determine if two variables have an association depends on what kind of variables you're working with. So we're going to start with the case where we're comparing a categorical variable to another categorical variable. And most of these tests, most of the procedure that we'll take is actually just a rehashing of hypothesis tests that you're already familiar with from Unit 3. So we're going to reframe some proportion tests as tests for independence in this section, 4.1. So let's get to it. You may recall that we looked at the following example from section 3.7 about Zocor, and whether or not it causes abdominal pain. And so just as a kind of a review question, what test would we run if we wanted to know whether the proportion of abdominal pain is the same in each group? So we've got 3 groups here, right? Zocor, placebo, cholestyramine. And the question is, what test would we run if we wanted to know if the proportion of abdominal pain is the same in each group? Well, the test we would run would be a homogeneity test. Specifically, the null hypothesis would be that P1 equals P2 equals P3. In other words, that the proportion of abdominal pain is the same for Zocor, placebo, and cholestyramine. And the alternative, of course, would be that at least one proportion is different. So in section 3.7, we talked briefly about how testing for homogeneity proportions is really the same as testing for independence. So to kind of get our brains around that a little bit more, let's ask ourselves what variables we would be comparing here. Okay, and a very common mistake is that students might think that, oh, well, the variables we're comparing are Zocor, placebo, and cholestyramine. But that's not true, right? Those categories, Zocor, placebo, and cholestyramine, those are just the various responses that are possible for one of the variables, right? The variable itself would be, in the case of these things, the variable itself would be medication taken. The variable here, for whether or not they experience abdominal pain, we can maybe just call that ab pain or something like that, right? And then again, right, experiencing abdominal pain or not experiencing abdominal pain are just the different categories that are possible to the ab pain question. So really the variables that we're comparing are medication and ab pain, right? Okay, so medication versus ab pain, right? Those are the variables. Now, if the proportion of abdominal pain is the same in each group, would the variables medication and pain be independent or dependent? Well, let's think about this, right? If the proportion of placebo patients, or let's start with Zocor, I guess. If the proportion of Zocor patients who experienced abdominal pain is the same as the proportion of placebo patients who experienced abdominal pain, and if those are the same as the proportion of cholestyramine patients who experienced abdominal pain, then clearly it doesn't matter what medication you take. The probability that you're going to experience abdominal pain is going to be the same. And so we would say that medication and abdominal pain would be independent variables. Okay, because again, the likelihood of you experiencing abdominal pain does not change with the medication. Okay, so if the proportion of abdominal pain is the same in each group, then medication and pain are independent variables. Okay. So then the next question would be, all right, how would we set up this hypothesis test in terms of independence then, right? So we already know that we can set up this hypothesis test in terms of proportions. We can just say P1 equals P2 equals P3. But how would we set it up in terms of independence? Well, we could say that the variables are independent as our null hypothesis, right? So medication and pain are independent variables. Okay, that would be the null hypothesis. The alternative hypothesis is that at least one of the proportions is different. So restating that in terms of independence, if at least one of the proportions is different, then that means that the likelihood of you experiencing abdominal pain depends on the medication that you took. So the alternative hypothesis would be that medication and pain are dependent variables. Okay, and so that's the way that we're gonna write out our hypotheses when we're testing to see whether variables are associated or whether or not variables are independent. And that might seem like a lot more work than just writing P1 equals P2 equals P3. Okay, but nevertheless we're just going to write it out in words like this. And actually, I think in most cases it is easier to write it out this way rather than writing out in terms of proportions. And I'll show you why. Okay, so let's look at some examples. So reframing homogeneity tests as tests for independence often results in a more accurate description of what's happening, and it's also usually easier. Okay, so looking at the Zocor placebo cholesterol thing, we could write the null hypothesis this way, right? We called this group 1, 2, and 3 before, so I'm using these subscripts Z sub ZA, Zocor patients who experienced abdominal pain, right? We want to see if the proportion of Zocor patients who experienced abdominal pain is the same as the proportion of placebo patients who experienced abdominal pain, and if that's the same as the proportion of cholestyramine patients who experienced abdominal pain. But notice that that only incorporates the top row of people who experienced abdominal pain. What about people who did not experience abdominal pain, right? So in reality, when we're running a homogeneity test, we're testing more than just this hypothesis here. We're actually testing this entire set of hypotheses down here. And so now, in this case, we're totally justified in writing out this simplified version of the formula because this condition is going to fail if and only if this condition fails, all right? That's true for this particular test, but it's not true in general, okay? Let's consider, once you start to consider tables that are bigger than like 2 by 3s, a table like this one, for example, that's a 5 by 4, okay? When you have to start to write out all of the various proportions, you can see that it becomes a huge pain to have to write, the null hypothesis in terms of proportions. And you might think, well, why can't we just use this simplified version? Why can't we just write the first thing? Well, it's the proportion of people with less than a high school education who are in excellent health is the same as the proportion of people with a high school education in excellent health, and so forth, right? If all of these proportions are the same, that doesn't necessarily mean that all of these proportions will be the same, because it could be the case that these are all the same, but that, these two things are swapped or something like that, right? So we can't just write out the simplified version. We would have to write out this whole long version here in this null hypothesis. And so stating things in terms of independence this way is going to be much easier, right? We would just say, well, let's think about the variables here. So I think our row variable over here is education. Clearly, right? Clearly it's describing some kind of level of education. And our column variable up here, this is supposed to represent health outcomes. So the null hypothesis would be that education and health are independent. Okay, it's worth noting that the null hypothesis is always that the variables are independent. Okay, the alternative hypothesis would be that education and health are dependent. Okay. So let me give you a couple examples. These will look somewhat familiar, but instead of running them as homogeneity tests, we're going to run them as tests for independence. I have failed to mention so far that those two things are equivalent, right? Like a test for independence and a test for homogeneity are equivalent things. But we're changing our perspective a little bit because thinking of them as a test for independence is actually slightly more accurate, and in many cases it's an easier way to write down the hypotheses. Okay, so let's do that. Right here we have smoking habits versus cause of death, and we're supposed to see whether smoking habits and cause of death are independent. Well, the null hypothesis would be that they are. Smoking and cause of death are independent, and the alternative would be that smoking and cause of death are dependent. Okay, so that's step one of our hypothesis testing procedure. Now, usually I would make you write down a bunch of proportions at this point, but let's simplify our lives and make this a little bit easier for ourselves, and we'll just skip that. We'll skip step two. But step three now would be to get a p-value. And to get our p-value, we're going to use the same app from Art of Stat, right? We're going to run a chi-square test. And we used to call this a test for homogeneity, but we're going to call it a test for independence now. And of course, we're going to enter the contingency table into the app from Art of Stat, and that'll give us a little p-value. So let's head over to Art of Stat and take a look at that together. So here in Art of Stat, we're going to go to Web Apps and then scroll down. I think chi-square tests are almost all the way at the bottom. Yep, here they are. And we want a homogeneity test, or in other words, a test for independence, right? So it's even telling you in Art of Stat that, hey, these things are the same, right? They're equivalent. We don't want a textbook example that we want to do our own. We've got a contingency table to enter. So let's see. The row variable, this is smoking habits. And the categories were smoker and non-smoker. Okay, and you can see it making the table over here and down here as well. We've done this before, right? Column variable would be cause of death. And categories were cancer, heart disease, and other. Now we can fill out this table. Okay, and if we got everything in there correctly, then we should end up with a good p-value. So it's good idea to double check that you got everything in right. And I think I do. I think I have everything in there correctly. So yeah, it repeats the contingency table up here, only it calculates all the totals for us and stuff. We've seen all of this before, right? The main thing we're here for is, of course, the p-value, right? 0.0154. So let's write that down. Okay, we can use that p-value now to make a decision. .0154 is less than 0.05, so reject H null. And now we can write down a conclusion. And again, we're going to state the conclusion in terms of independence here. We're rejecting the null hypothesis, okay, in favor of the alternative. So we'll go ahead and say that smoking and cause of death are dependent variables, right? Okay, now let me just say a word about the way that you write down your conclusion. Sometimes it's tempting to want to make a stronger statement than what the test actually allows us to make. In this case, I think it would be justified to make that stronger statement, but it's not always justified. So let me explain what I mean. I think it might be tempting here to say there is sufficient evidence to conclude that cause of death depends on smoking habits. In other words, there's sufficient evidence to say that the way you die depends on whether or not you were a smoker. Because obviously, smokers are at elevated risks for cancer, right? And other kinds of diseases. So yes, in this case, I think you would be justified in saying that. But you're not always justified in making that stronger statement, because there's another possibility, right? The other possibility here doesn't make sense, but sometimes it does. So the other possibility would be that your smoking habits depend on your cause of death. The reason that doesn't make sense here is because it's not like you know how you're going to die, and then based on that information you decide whether or not you're going to smoke, right? That's not the way that it works. It's the other way around, right? The way that you die depends on whether or not you smoked. But again, in a lot of situations, right, the logic could flow the other direction, and the test actually doesn't tell us which direction it should flow. And consequently, I think it's always safer to just write your conclusion this way and say, yeah, there's sufficient evidence to say that the variables are dependent. Okay, which variable causes the other one to happen, right? Which variable is explanatory and which variable is response? Well, the test actually doesn't tell us that, right? And it's possible that neither of them causes the other one to happen, right? It's possible that neither of them is explanatory or response. It's possible that they're both responses to some third hidden kind of lurking variable that we're unaware of. So anyway, better to just say that the variables are dependent, okay? They change together. Okay, let's look at another one. So education versus health. Let's run the test here. I'll let you pause the video and write out the null and alternative hypotheses. Okay, so that's my solution for the null and alternative hypotheses. Then we're going to run the test, right? Step 2, we're going to skip. We'd have to calculate 20 different sample proportions, and I'm not going to make you do that, right? So we'll skip that one, but we'll go on to step 3 and get the p-value, okay, by running a chi-square test for independence. Okay, so I'll let you run that test and then check in with you and see what we get. Okay, and if you get all of that in there correctly, you should end up with a p-value less than 0.0001. Okay, so let's go ahead and write that down. Based on that, you can make your decision and write your conclusion. I'll let you pause the video and do those things. So here's my solution. We're rejecting the null. We have a small p-value, right? So there's sufficient evidence to conclude that education and health are dependent variables. They're contingent, right? Now, this is a good example of where the logic could flow in either direction. On the one hand, you might be tempted to say, oh, well, your level of health depends on your level of education. And maybe your reasoning is that, well, the more education you have, typically the more money you make, the better your benefits are, and so you're able to afford better health care. And so the more education you have, the better your health outcomes. But you could argue the other way around, right? You could say, well, actually, no. If somebody is in really good health, then they have more opportunities to pursue education, right? And so the better your health, the more education you have. And it's not clear, the test itself doesn't tell us which variable drives the other one. It just tells us that they change at the same time, right? Like, in other words, it tells us that there's some kind of relationship between these variables. There's an association, there's a dependence, right? There's a contingency between these variables, but it doesn't tell us which one causes the other one to change. So I think the safest way toward the conclusion is to simply say, right, that there's sufficient evidence to conclude that education and health are dependent variables. Okay, now I want to talk about how to explore association between two variables when you're dealing with raw data. Okay, because that's what you're going to encounter in one of your projects. You're going to have a bunch of raw data, and the raw data does not appear in a contingency table, right? This is a contingency table. This is the way that we are accustomed to seeing the data show up in the problems that we've looked at. But in reality, in the real world, when you go to collect data, usually it doesn't show up that way. This is like a summary that's been prepared for us. Usually the raw data looks like this. It would just list off the possible it would just list off the responses for each variable. So in a set of raw data like this, each individual in this or each row in this table represents an individual. So this is a person who has a graduate degree and is in fair health, right? This is a person who has a high school diploma and is in poor health, right? This contingency table over here, it just summarizes the raw data. So when you're starting with the raw data, you'll have to use a different menu in ArtofStat, right? So ArtofStat will take raw data and it'll convert it into a contingency table for us, which is really nice. There is one potential caveat that ends up actually not being a huge problem, and that is that if the contingency table that you get ends up being a 2x2 table, then you really shouldn't run a homogeneity test. You should run a two-sample proportion test. But the good news is that ArtofStat recognizes that and it makes the necessary adjustments automatically, so we don't really have to worry about it. So we'll just feed the variable, the raw data, directly into ArtofStat. And to do that, by the way, you just go down to individual observations, and then you have this place where you can put the data for variable 1 and the data for variable 2. So for the next couple sets of examples, you should have this data for 4.1 open up so that you're ready to just copy and paste this stuff. It's going to be much easier than sitting there and typing in, hundreds of different values, which you probably don't want to do. Anyway, so without further ado, let's look at a couple examples. So this example 2 says, a professor collected information about the students in his class regarding whether they are left or right-handed, where they sit in class, front, middle, or back, and whether they took a practice test before their last exam. His data can be found in the data for 4.1 workbook. Test at alpha equals 0.05 to determine if the following pairs of variables are independent. Show the contingency table and the hypothesis test below. Okay. Very good. So for part A, we want to compare seat position versus practice test. So I'm just going to take you over to the data. Seat position versus practice test. Okay, so we want to compare these two columns. So I'm going to start off by copying the first column, and then I'm going to go over to ArtofStat, and I'm going to go to, let me just start over, right? We're going to open up the chi-square test. We want the test for independence, and we want to use individual observations, okay? And then I can paste the data into that first column, okay? I just used Control V to paste it. This was your seat position in class, right? That was the name of that variable, seat position in class. So that's what we'll call it. The name of the second variable was whether or not you took a practice test. So I'll say practice test question mark, and then copy and paste that data. And then once you have that, you can hit submit, and it makes that contingency table for us, which is really nice. Okay. It also computes a p-value, and the p-value here is very large. It's telling us, yeah, there's really not much of a difference where you sit in class. Where you sit in class really doesn't tell you whether or not somebody was more or less likely to take the practice test. You can see that reflected in the bar chart as well, right? The proportion of people who didn't take the practice test versus the proportion of people who did is relatively the same whether you sat in the back, in the front, or in the middle of the class, right? So there's just not much of an association between the variables seat position and practice test. Okay, so let's write all this stuff down. First of all, we've got to copy and paste this contingency table. I'm just going to do it by hand, and you don't have to give me the totals or anything, but I do definitely want to see these numbers here. Okay, so we had seat position, back, front, middle, and then we have whether or not they took the practice test, yes or no. Okay, so there's the contingency table, right? If you wanted to, you could feed that into Art of Stat, but you're going to get the same p-value, okay? Our null hypothesis was that seat position and practice test are independent, and the alternative was that seat position and practice test were dependent. We ran the test by running a chi-squared test for independence, and we got a p-value of 1, which is very large, right? We usually don't see a p-value that large. But in this case, there's such little difference. There's almost no difference in the distributions that, whoops, I put 0, I meant 1. But there's almost no difference, so the p-value is 1. Okay, so our decision, well, 1 is not less than 0.05, so we do not reject H null. And then for our conclusion, we can say something like, there is not sufficient evidence to conclude that seat position, or maybe we'll just say that where you sit in class and whether you take the practice test have anything to do with each other. Or we'll just say that they're dependent, right? There's not sufficient evidence to conclude that where you sit in class and whether you take a practice test are dependent variables. Okay, the evidence seems to say that they're probably independent of one another. Okay, let's do another one. Handedness versus practice test. So same scenario, right? This time we want to look at whether or not your handedness affects whether you took the practice test, right? Are left-handed people more likely to take it or something like that? Well, there's only one way to find out. So we'll run the test. Let's select the data, copy it, and refresh the page so that we can run a new test. We have handedness and practice test. So pasting the data there. Copy. And paste. And then hit submit. And another very large p-value. Once again, we're going to say, no, there doesn't seem to be much of a relationship between these two variables. Okay. So let's write that down. First of all, the contingency table. Oh, notice that it's a 2 by 2. So really what we should do is run a 2-sample proportion test. But if you did, you would get the same p-value. There aren't that many left-handed people to begin with, right? So it's kind of a small sample size. Anyway, these are the hypotheses for the test, right? Handedness and practice test are independent versus handedness and practice test are dependent. We ran the test and got a p-value of 0.9145. So our decision, 0.9145, is not less than 0.05. So do not reject H null. And then our conclusion. Okay, there's not sufficient evidence to conclude that handedness and practice test are dependent variables. Okay, so that's how these things go. Now I do have one more example, I think because I wanted to give you an example where we did reject the null hypothesis, but also because I think you could go ahead and run this one on your own. It says nearly 1,000 college students were asked about their stuffing preference at Thanksgiving. Their responses, stratified by gender, can be found in the data for 4.1 Excel workbook. Test whether stuffing preference is independent of gender at the 0.05 level of significance. If there's a statistically significant difference, compare the observed and expected counts and describe the difference. So we have a little bit of a follow-up question we'll do there. Let's look at the data. This would be the stuffing preference. We want to compare gender and stuffing preference. So I'll let you pause the video and go ahead and run that test. You don't have to write down the contingency table on this one, but just go ahead and run the test. Okay, here are my solutions. So the null and alternative hypotheses, obviously gender and stuffing preference are independent versus gender and stuffing preference are dependent. When you run the data through Art of Stat, you get a p-value of 0.0151. And it's really, this is a huge data set. There's almost 1,000 individuals. So it might take you a little while. Like you might try to copy and paste the data and then it takes Art of Stat a second to think about it because there's so much data there. But because we're getting a small p-value, we reject the null. And so there's sufficient evidence to conclude that gender and stuffing preference are dependent. Once again, I think you could make this statement a little bit stronger because I don't think that your gender is going to change because suddenly you decided that you prefer rice-based stuffing, right? It's probably the other way around. Like for whatever reason, women have different preferences than men, as far as stuffing is concerned, anyway. So we did indeed find that there was a difference, and consequently, we now have to compare the observed and expected counts to try to describe what the difference is. So let's head back over to Art of Stat. So we can look at the expected counts and the residuals. Those would be useful, okay? Because the residuals are just the observed minus the expected. So we can see what the differences are. It looks like the biggest difference is with rice-based stuffing. There were about 10 men who preferred rice-based stuffing above what was expected, right? We observed 10 additional men, more than we expected, liking the rice-based stuffing, whereas for women it was 10 fewer, I suppose, right? So that's kind of interesting. So I guess the main difference is that women are more likely to like bread-based stuffing, and men are more likely to like rice-based stuffing than what we expected. Now, with that said, look at the bar charts. I mean, whether you're female or male, you're far and away more likely to say bread-based stuffing. Most people say that they like bread-based stuffing, right? By a pretty large margin. However, men are a little bit more prone to liking rice-based stuffing than women are. So I would say that's the major difference. Okay, so it seems that men are more open to rice-based stuffing than women, and that's that. So that'll do it for section 4.1. In the next section, we'll look at how to decide if two variables are associated when both of the variables you're comparing are numerical rather than categorical, and that will require us to introduce a new kind of hypothesis test. But that'll do it, at least for categorical versus categorical comparisons. So thank you for hanging in there, and I'll check in with you again in section 4.2.